to do something rather different with the adjoint method, but I'm going to demonstrate the adjoint method on the case of a partial differential equation. Describe the adjoint method by discretize for a sequence, a long sequence of arithmetic operations. Now I'm going to demonstrate it in the case of a partial differential equation. It is actually mathematicians, people who study partial differential equations from a mathematical point of view, do use adjoint equations for their own purpose, for proving theorems of existence and things like that. They do use that as a tool, a very standard tool, even of pure mathematics, only of applied numerical computation. And also, since most our problems are based on physical laws which can be described, usually described by partial differential equations, it might be useful to look at what the adjoint method is in terms of partial differential equation. And it was my plan to prepare that this morning, but it happened that yesterday I had a talk with Kwanle, is it here? Yes, okay. Okay, and found that it was particularly appropriate to speak of that now. Especially for people who like Kwanle use adjoint equations for problems which are different from methodology of construction. Okay, so the equation I'm going to consider is the standard heat or diffusion equation, which describes a temporal evolution of temperature along take a one-dimensional domain, and we take a two or three or multi-dimensional one. That it will not be different. Because only make the notation slightly more complicated. I take, so for instance, I can consider a metal bar with extremities at position x1 and x2, which can be heated at either end, not in the middle, instead of cooled, and we can possibly regulate the temperature at either end of the bar. And you want to know how the temperature will go. Well, the temperature, if K is its complete coefficient of its diffusion, it will be able to, according to the equation, d of temperature relative to time equals K times the second derivative of temperature with respect to the coordinate x. That's well known, and it is also well known that this leads to a well-posed problem for if K is positive. This leads to a well-posed problem for integration into the future, but not into the past. And this corresponds to the fact that heat diffusion is physically an irreversible process. So there is kind of morality in the sense that there is agreement between what physics say and what mathematics say. And so to be more precise, I consider the evolution of temperature over a time period T1 and T2. And I am interested in how I can control the temperature in the bar by defining appropriately the initial condition for temperature and also a lateral binary condition for temperature, because I assume that I can act on the bar at each of those two ends. I can act on it at the initial time and then at each of the two ends. And so, people who know about partial differential equations tell us that the solution to this equation is completely and uniquely defined by the specification of t at the initial time for all x's and t at all times at position x1 and x2. You can specify those as you want with the conditions of t here on the one side, as you want, and this completely defines the unique solution. It is not the only way to completely define the unique solution. There may be many others, but it is the principle. So, what I'm going to show, among other things, is that the adjoint equations are a basic tool for solution of control problems. Control problems are generally a problem in which you want to act on a system, a physical system, a biological system, system, societal system, human society, and you want to act on it, to lead it, for instance, to the state you like it or would like it to be in, but you can act it, you cannot act it exactly as you want to have it. There are limitations. For instance, device, contraction, machine, some physical boundary. You know it's inner working, but you cannot act on it inside. You can only act on the boundary, like here, by exerting mechanical action, heating it, cooling it, no stress up there. You can act on the boundary, but not inside. Still, you want to put your system in a particular state. A magnificent example of control, the control problem, is controlled nuclear fission. Physical processes by which hydrogen atom fuse together to produce helium atoms and to produce, in addition, energy. This is what happens with the sun and the star, and the origin of the energy emitted by the stars of the sun. This has been done by human beings in an uncontrolled way, in the form of hydrogen bonds, but uncontrolled by the liberation of energy, which is what is it, which is uncontrolled. So, people were of controlled fusion, of which number of people said, if it becomes technically and economically possible, and people said that we basically solve the problem of energy which human societies are facing at present. What I can say, that about now 50 years, but it is announced that controlled nuclear fusion will be available in 50 years. People work on that. International hydrogen project. So, what is controlled fusion? There is a plasma of hydrogen atom. It is impossible to act on that side. We can act on it only, basically, maybe what I'm saying now is not physically perfectly correct, but what I know, by creating outside of the plasma an electric or a magnetic field. And it's through electric and magnetic field that one can act on the plasma. I spoke in the first lecture of inverse problem, and I spoke the problem of determining the state of the plasma from observations of electric and magnetic fields. I speak now of what can be called the adjoint problem, that is how to impose a magnetic and electric field in order to lead the plasma into the state we want. That's very good activity, effectively for control. So, I want to be speaking about nuclear fusion. There is nothing much more elementary, but here we go. So, mathematicians tell us, you specify it, and this defines a unique, complete, unique solution and equation. This boundary, which I have drawn right here, I will call the input boundary, gamma I, and so a complete solution is defined by the definition of what I call input in the system, that is the specification of I, of T along the input boundary, gamma I. Gamma I is what is written in the definition is right here. And my problem is how to act in temperature in order to obtain, for instance, a given temperature distribution. So instead of what I could do that for obtaining a given temperature distribution, in order to make some analogy with assimilation, I consider that what I'm interested in, I consider I have distribution T hat of observation over the whole domain D here, and I want to minimize, to obtain such a field such that the quantity J equals the integral of the square difference E minus dx squared over dx and dt is minimized. Okay. This is what I've prepared, so this is what I'm waiting. Of course, I could limit the question to determining a temperature distribution at the end temperature T2. As you will see, secondary. The exact form of the quantity I want to minimize or maximize is actually secondary. It is important, of course, but in the derivation I'm going to do is actually secondary. Okay, so what's what I want to do? My problem. So J, the temperature, is a function of the input Q through the solution of this equation, and then J is a function of the temperature. So again, same time. J is a combined function of the input U. And I want to determine directly, I want to skip the dependence on T and to determine directly how J depends on U. It's in a sense the same problem which I stated, for instance, in the joint equation yesterday. So, I consider a small perturbation delta U on U. This implies a perturbation delta T and T, which formally is delta T given by D of delta T over T equals K, second derivative of delta T with respect to X. But the same equation are above, because the equation is linear. Absolutely formal to write that. But if your equation there was non-linear, then the equation for the perturbation, which is called the tensor linear equation, would be different. And for those, and for those who are interested, I think I need all four blackboards. All four whiteboards.
You cannot see that, right?
Can you? Oh, yes, sir. You would have been. Okay, so I try to get this is formally identical to that, because that equation is linear. But if that equation was non-linear, then the perturbation equation would not be identical with the basic equation. And for those of you who are interested, I have a paper here we can give you, in which I do what I'm going to be doing now on a non-linear equation. I'm not doing it now because I will need still more work. But linear reason, and more time, but not non-linear reason. It can be done for a non-linear equation. Well, I can find. If I have an equation of a form, for instance, this is d over dt plus u du over dx equal k second derivative of u. This is actually the equation on which I have on this paper. This is nonlinear, and this is the reason you can do d over dx on 1/2 u squared. And then the perturbated equation for that is d over delta u, d over dt of delta u, plus d over dx of the perturbated version of that is u delta u equals k second derivative of delta u with respect to x. And this is not of the same form as that, and in particular the u in the vicinity of which the perturbation is done is still present in the perturbation equation. So it's a more complicated situation, and this is the situation which is described in the paper I have. So just to stress that I've taken a simplified linear case, but what the approach I'm going to describe can be extended to the. So this perturbation delta t implies the perturbation delta j, which is equal to j equals integral over t. Now I do a differentiation as elementary as it is. 1/2 here. So, and I differentiate that, so I have t minus that times delta t dx dx. That's the perturbation on J, resulting in the perturbation of T, that results from the perturbation of U. And now, and I will say that I've solved my problem if I am able to write that delta J as delta J equals integral where along the input variable, the input boundary of some quantity gamma times delta U times S, where S is the length element along the boundary. If I am able to find the gamma such that delta G depends explicitly on only the original delta U, then I will say I have solved my problem by showing explicitly how J depends on U. Of course, but I know to act on U for gamma in order to modify J in the direction of I want. I'm capable of controlling J by acting only on U and by acting only on the boundary of the system. So that's my purpose. So what I do now is something which may seem highly irrational. T minus cat dt delta t. Dx dt. Well, I'm not going to carry definitely the dx dt. Integral of t, it will be implicitly obvious, but it is integral of that. And then I add this quantity. Add d over dt d over delta t over d minus k second derivative of delta t minus x. That I multiply that by some quantity lambda x of t, and I do the integral. That's true. This quantity is 0. So that's true. Delta t is still equal to that. Of course, yes.
Is it like something like constraint minimization done with Lagrange multipliers?
Yes. But lambda is a Lagrange multiplier. I've just said it, but I was going to say. But lambda is a Lagrange multiplier. In fact, the adjoint solution is a Lagrange multiplier. So this seems totally irrational. In fact, I introduced a quantity which, at this stage, is totally unknown, and I multiply it by 0. The first thing I have to do at quantity is multiplying by 0. What's interest? Well, I told you that's the idea, but je left with Lagrange around 1770 or 1780 at the young age of 15. And he wrote to Gauss, and he said, what do you think to Euler, and so he wrote to Euler, and what do you think of that? And that's a good idea. And so that's so now I'm going to do a number of manipulation on this expression in order to put this expression into that form. And so what I'm going to do is to do systematically integration by parts. So I take here lambda d of the identity of the dx. Integration by parts is the magic way of deriving adjoint partial differential equation. Lambda d over t equal, of course, d over t lambda t minus d lambda over t delta t. I do the same thing with second term. So I ignore the minus sign, I ignore k, since I was side of the term. Lambda second derivative of x derivative of x d over dx lambda x minus d lambda x d over t. The idea is to integration by parts is to take the delta t's out of the partial derivatives in order that they become factors as the here. And again, I bring new derivatives. So this d over x lambda term, d lambda t minus plus. And I try all that there. So, check. We have farther view and me from the board, so if I make a mistake, you are in better position to detect it than I have. So I carry this expression into that. And I still gather the terms. So they are boundary terms, which is here, here, here. And the other terms are not boundary, or not boundary terms. Terms with which we obviously we can boundary terms on integration over D. They are not boundary terms here on this.
Can you write it bigger next time?
Oh, bigger? Okay.
Getting small.
Okay, it's a little too small. Yes, definitely the term that I have a very bad handwriting. So it's fault. When I was a boy at school, the teacher was not very pleased with what I was a main method. It does not improve. So I gather all terms which are integral over vitamin B. And these terms are different. Well, the term which will not take comparison. This term and this term and this term. They are all proportional to delta t. So I put t minus hat. Here I have this, which comes with a minus. Yes, the minus sign I put there is of course arbitrary, because lambda is undefined, but it turned out to be convenient. So put a minus. So I add minus, so I have plus. Minus, yes, so plus d lambda over t. And here I have plus k, so it will make plus k, second derivative of lambda with respect to x times delta t integrated. Is that
Delta t.
agree now?
Instead of dt, it will be delta t.
You're right. Okay. So then there is that term which is integrated with respect to both x and t. The integration with respect to t, yes?
And the sign's right actually.
The sign is not right.
Okay, yeah.
T over t minus at. I put a minus sign here. So I have lambda t minus minus. This must give a plus. In fact, the important thing, I'm sure I'm right, is that now, instead of having d over dt minus k second derivative, d over dt plus k second derivative. And this is what I want. So, I think it's right because here minus lambda derivative of delta t. So minus.
Yes, I understand.
Okay, so I have this term with the minus sign in front of it. But the integration with respect to t, inside would mean that I have an integration from x1 to x2, and it will be minus of lambda delta t, depend between times t1 and t2. Because when I integrate this term in time first, I obtain the integral of and I obtain an integral over x of lambda delta t at time t2 and integral over x at time 2. You agree? So this term now, so the other two terms I have to this one. Then this is an integral with respect to x. So this term comes with plus k. Plus k minus this term are in here, so it comes with plus t. So I will have integral from T1 to 2 of lambda d over delta t over dx d over delta t dx. Integral of x equals, no, integral of x. Here, integral of x, delta t, integral of x. Here, integral of x t, is again between the boundary x1 and x2. So the first thing I do with that is to integrate with respect to x. So from this term, taken between x1 and x2, and then integrate with respect to time. So this term, which has the opposite sign, minus k, same thing, d1 over 2, d lambda over dx, delta t, dx, dt, taken between x1 and x2. Is that all right? Do you agree with that? And that is true for any lambda, whatever lambda here I use is. So now I choose lambda so as to reduce this to that. This is my final purpose. Oh no, if I retire, you will not see because of the shade. So
Maybe it really stops it with plates, yeah?
what do you say?
Maybe stops it once, so that we don't need to see everything from the
Okay, I did that right. Okay, so I want to get rid of this term. This term. It's not of the form I want. The form I want right here is delta G, boundary, gamma, delta U, yes, along boundary gamma 1. And we're going to put values. This is not space-time is zero, so we don't want it. So I enclose that d lambda over dt, but j, second derivative of x to respect to lambda, plus k minus t hat. So this eliminates this term. Now this one, lambda dt over dx squared. At time t1, this term is alright. But at time t2, it's not alright because t2 doesn't belong to my input boundary. So I equals that lambda of x and t2 equals 0. So this eliminates t2. This term, well, typically, I don't know that in the special derivative of delta t, I don't like it. So I enclose that lambda equals 0 at x1 and x2. Lambda x1 equals 0. Lambda x2 equals 0. So this eliminates this term. And that, well, the term is alright. It is proportional to delta t along the lateral boundary condition. So it belongs to what I want to have. So this I'm left with delta g equal this term, that is sum from x1 and x2. Now I put explicitly lambda of x t1 delta t of xty. Yes? And it's plus because there is a minus, but there is another minus because it is the lower boundary of the difference. Minus, of course, I took the term of T2, minus K integral from T1 to T2 of d lambda over dx position x2 time t. See? Delta t, of course, delta t, of course. Plus the same term, the plus sign, at position x1. The lambda over x, t, delta t, is meant to be x2. I will choose like either way else. Do you agree? That's it. But in integral, it's in my input binary. 1, 2, x1, 2. What is an integral of delta t times something along this part of the boundary? What is an integral along which part of the time of delta t along which part times something? And that is an integral of delta t along this part of the boundary times something. So my gamma, the quantity I want to control my temperature along the boundaries, is given by lambda here minus k d lambda of dx d lambda over dx here and plus k d lambda over dx here. Okay. Is there such a lambda which can satisfy such conditions? Is that possible at all? Yes. This equation is just the heat equation with a forcing term. What? With k which is same sign, so that it is appropriate for integration into the past, not into the future. So imposing a final condition on it is perfectly appropriate. And then in addition, I impose the lateral boundary condition in agreement with what mathematicians say, but for writing the equation, for this kind of equation, we must define an initial condition and lateral boundary condition at all time. An initial condition at all points in space, and lateral boundary condition at all times. Which is exactly that. Very different, which is appropriate for backward integration. So how do you obtain my lambda? And how do you control the whole thing? For given initial temperature, I integrate this equation. Then I integrate that equation, which of course is the adjoint equation with final condition lambda equals 0 and lateral boundary condition lambda equals 0. It's going to be simpler. But with a forcing term, same as that. But because if the forcing term is 0, then I obtain a non-zero lambda. And the partial derivative, because that is that, of j with respect to initial conditions is given by lambda, and the partial derivative of j with respect to the lateral boundary condition is given by k times d lambda over dx plus k or minus k, depending on which side, or which side I consider. That's all. I know how to control the temperature in my bar. And of course, I could use it by taking not an integral of T over T hat, but taking only, actually, to be a more realistic problem, in order to control the final temperature of the bar. And then I would minimize, I could do that. Then if I did that, instead of having a t minus t hat, which acts constantly of time, I would have a t minus t hat, which would act only at final time. And I could assume that I don't have a complete control, but I control the temperature only on one side. Well, I would do the same thing, but there is one control I could not use. I may not be able to reach a given temperature at the end, but I want to be able to obtain the final temperature, which is as close as I want to T hat. So that's the demonstration of how to use the adjoint method, that is actually Lagrange multiplier, but the Lagrange multiplier for in-control problems. And in a sense, this is what we do when you do variational assimilation in order to obtain gradient, but actually it's also a control problem, because what we do when we do variation assimilation is to control the initial conditions of the model so as to fit as closely as possible the observation, so as to minimize the objective function. Which is a control problem, not a physical control problem, a numerical control problem, but it is a control problem. And algebraic equations are the general tool for control problems. In fact, became widely known and progressively, knowledge progressively propagated to other films by a book by, I guess it has been a French mathematician, Jacques Lyons, who wrote in 1968 or something like that, a book which applied mathematician, which is optimal control of partial differential equations or something like that. It is essentially that, in the addition, but it is mathematically totally proper, but he considers specifically on which functional spaces this is accepted. But very plainly, not only this demonstration is derivative, but discussion how, well, which condition this observation is strictly valid or not. And this is a similar thing has been done in Russia in the same time, in particular under the leadership of the mathematician G.I. Marchuk, who was doctorate in the School of Applied Mathematics first. He was, Marchuk was an important man, he was Minister of Science and Soviet and Russian Academy of Science. Very important man. Soviet, Russian scientific expedition. He's still alive and active. He also died a few years ago. So that's a few comments. Let us suppose the temperature shows as real T over T hat. Then the force in term here will be 0. So because of these boundary conditions, lambda will be 0 everywhere. And the gradient, this will be 0 everywhere. Which means that T equals T hat corresponds to a stationary point of the function I want to minimize. And something else, yes. This basic equation is okay for integration into the future. The adjoint equation is okay for integration into the past. That can be easily understood. If I have this equation, it means that whatever the initial condition, the final condition is the same. The equation itself will tend to uniformize temperature along the bar. Not faster than 1. So for the same average temperature, the final condition will be at infinite time, will be independent of the initial condition. So the farther I go into the time, the smaller the sensitivity of the final condition with respect to the initial condition. Because essentially, at last time, the state reached by the bar is independent of the initial condition. When I do adjoint integration, what I compute, what is to take a fixed final time, and I compute sensitivity of the state, the final state, with respect to the initial state. But the longer I go backward in time, the smaller the sensitivity must be. Because the longer the integration time, the smaller the sensitivity of the final time with respect to the initial time. So whether I keep constant initial time and moving final time or the opposite, the result is the same. The sensitivity becomes smaller and smaller. So the adjoint integration must be dissipative for backward integration, which is exactly what we're finding. Technically, it's written for the fact that this is a first order derivative. So I do one integration by part and one change of sign. This is the second order derivative. So in order to eliminate, to take the delta t out of the derivatives, I must do two integration by parts. That is two change of sign. And therefore, when I get the adjoint equation, there is a change in the sign. What else? At the minimizing solution, if I minimize, solution, lambda equals 0 here, lambda equals 0 here and there, and lambda equals 0 here, because lambda along this part of the boundary is the gradient of J with respect to the initial condition. So the minimizing solution, if I minimize, it is 0. So the minimizing solution is characterized by the property that lambda equals 0 all along the boundary, everywhere. Third remark, along the lateral boundary condition, the lateral boundary condition are present in both the direct integration and the adjoint integration. Thus, times t equal to t1 is the boundary condition and the condition for one integration. T equals t2 is the condition for adjoint integration. The lateral sides are conditions. We must specify conditions for the lateral sides for both direct and adjoint integration. So along the boundaries, you have two things. You have the boundary condition for lambda along this lateral side, higher, and you have the sensitivity of J with respect to the input along the boundary, which are plus and minus, depending on which side you consider, k d lambda over dx. Of course, x in general will be different from 0. So along the boundaries, you have two things. Lambda equals 0, which is imposed by the adjoint equation, and d lambda over dx, which is the gradient you look for. So two things along the lateral boundary, two quantities of interest along the boundary condition. First thing, let us suppose I will change the definition of my initial J for something else. All of that I do here will become stable, except this term. So I get the same equation here with simply another forcing term. So the forcing term, so the quantity I want to determine the sensitivity of appears in that derivation only through the forcing term of the adjoint equation. The adjoint equation is the same. And the boundary conditions of the adjoint equation are the same too, independent of which quantity I want to determine the sensitivity. And independent also of with respect to what I want to determine the sensitivity. The question of with respect to what I want to determine the sensitivity is actually is something which is determined from a lambda. Once I've solved the adjoint equation, then I take a lambda, and depending, mainly not absolutely obvious here, but depending on with respect to what I want to take the sensitivity, I have to do something with a lambda. For instance, I may be interested in determining the sensitivity with respect to k. I may have a k which is function of x, significant coefficient, which is not the same. The bar may not be homogeneous. Then I would like to be able to determine the sensitivity of J with respect to k, considered as a function of x. well, the adjoint equation I have to solve will be the same, but then the sensitivity will be another combination of lambda. That's a deal under the not from fine. So there are actually basically three components. There is the basic equation and the condition that are necessary to specify a unique solution to the equation. I've chosen to take this boundary condition, but they could be internal conditions. Actually, in assimilation of meteorological observation, the conditions we impose are observations within the domain, in a sense. So these are internal conditions. We don't have boundary conditions when we integrate them. We have observations within the model, within the domain. So there might be internal conditions. They have a condition, but I want temperature at a given point to be this or that. I want to control from the inside. It's not impossible. So there is a basic equation. The quantity, the sensitivity of which I want to determine, and the quantity with respect to which I want to determine the sensitivity. These are three different components, which are essentially independent. And all three come up in the adjoint approach at different points, at different parts. The basic equation appears through the homogeneous part of the adjoint equation and the corresponding associated boundary condition. The quantity I want to determine the sensitivity of comes up through the forcing term in the adjoint equation. And the quantity with respect to which I want to determine the sensitivity appears in what I do with the adjoint solution once I've determined it. So these are three different steps. And this is the same thing when you do variational assimilation. Although in the code, those three steps may not be absolutely the distinction between them may not be absolutely obvious in the code, but still they are there. Okay, so that's all. Thank you. Well, I was fortunate I did not do it non-linear case because I wouldn't have a linear side.
Probably good to have that also in written form.
Well, in written form, I have the paper, in which contains actually more than that.
Yes.
So maybe
yeah, then we can put the link of that into the page. The same is true of the lecture notes, of course, they will appear. Many of them will appear on the page. Yes, good. Further questions? Yes, please.
Just a technical question.
So, I have a question. Does it answer your question? You sent me a question this morning by mail. Okay,
well,
okay, now go on.
actually, my question is like very technical. When you're coding the discrete adjoint,
yes.
How do you impose the boundary condition for the discrete case? Like you transfer
Lambda equals 0?
Yes.
Well, it may depend how the boundary conditions are imposed in the direct model. But
yes.
actually, it may even be implicit. It may be, this boundary condition may even be specified by not putting an explicit term in the equation, since it is 0. You may have, for instance, this lateral lambda in this equation, in the discretized equation, we'll have a finely differential scheme for that, which will be typically something like lambda at time I plus 1 minus 2 lambda at point I plus lambda at time I minus 1 over delta x squared or 2 delta x squared, or delta x is the distance between two neighboring points. We have something like that. And there the condition will be that lambda I plus 1 equals 0. So either you write explicitly in your code lambda I plus 1 equals 0, and you use the same expression for all the points, or you put special expression for the endpoints, and then you just simply don't put a lambda because it is 0. It could be like that, but this lateral boundary condition is important. If in your code, with second derivative with respect to x, It is with respect to lambda, actually. The second derivative with respect to lambda is written in that form.
So basically, it means for the discrete case, the Laplace operator you actually wrote down is like a tridiagonal matrix, like it's symmetric.
Yes.
You just simply transpose it.
Yes.
Okay.
Actually, transposing it means taking the same, because what I've written here is symmetric. So as I told you, as I said in my previous lecture, if you have a symmetric operator, a symmetric linear operator somewhere, it's adjoint, it is identical with its adjoint. So the delta element to modify it. So the second order of the differentiation with constant delta x, with uniform delta x, is symmetric. The matrix was represented is obviously symmetric. It's -2 along the diagonal, +1 on the other side of the diagonal.
Okay.
With periodicity, no, not with periodicity condition, in that case. Actually, if you blindly apply the rules I mentioned in my previous talk, you will automatically, you can look at the code and I'll show you. Actually, I can take one step further. If you write an adjoint code using the rules I described at the end of my previous lecture, you must first specify that all, you must, it's not compulsory, but it's very convenient to specify to start with that all adjoint variables are 0. You set all adjoint variables, the one which I call adjoint of A, adjoint of B, adjoint of C. You just, to start the code before starting the integration, set all these variables equal to 0. And this will imply, among others, the lateral boundary condition. And then if you do that, you're safe.
But that is a unique choice of my Laplace multiplier, is it?
That is a unique and non-unique.
I mean, what you mentioned, the boundary condition for the adjoint field lambda.
Yes.
Then that is a unique choice, is it?
Oh yes, oh yes, it comes. Yes, but it may not be unique. Well, if your objective function is itself defined along the boundary. If I want to control the temperature at the end, at time t2, I want to act in my system to control the temperature in the bar at time t2, then the condition, this term t minus t hat, will be present only at final time, which is in a sense almost equivalent to specify an initial final condition. But you don't have to worry about that. If you write the mathematics, then you have to introduce a delta distribution. Strictly speaking, you have to speak not as function of a distribution.
Yeah.
If you write a code, then you may either decide the lateral or final condition is 0, and then immediately change it, or write from the start that it is not 0. That is in the case when there is on the objective function terms which are defined along the boundaries. Of course, if the objective function is the sum of the grid points, the sum may contain terms along the boundaries. But again, this will come out automatically. If you apply the rule I've described mechanically, blindly, it will come out automatically. You don't really have to worry about that. If you want, you can take a piece of code and illustrate it.
Thank you.
You don't have to pay. It's not a real concern. I understand you. You're asking the question, but my answer is it's not a real concern. When you look closely at it, you find out that it's solved automatically.